are you ready to start? Pancho?
Yes.
Okay.
Yes.
Yeah, please start.
Thank you very much, Professor Wada, for your introduction. Thank you very much all for joining my presentation. And I will be presenting our work on the following topic, as Professor Wada already mentioned. I'm Pancho Dachkinov, a doctoral student in Professor Hiroaki Wagatsumo's laboratory. So this is the content of my talk. I will introduce briefly our idea, discuss the problem, then go through the literature review, what has already been done, what solutions exist, and what gap is available on the market, what can be improved. Then I will go through the methods and results, then discussions for future development of the project, and I will conclude the talk. Firstly, this is a brief summary of our idea. We are developing assistive supportive device for the knee joint that is based on a compliant mechanism that will be integrated into the supportive device. In order to achieve that, first we need to understand well the biomechanical behavior of the knee, the kinematics and kinetics of the joint, then use these as requirements for the design of the compliant mechanism. And after that, integrate the compliant mechanism into the orthotic device and verify the results with the attached device to the human knee. So this is the main goal of our work. And what is the problem? Knee injuries are very common. As a matter of fact, between 20 to 40% of the injuries are at the knee, and the anterior cruciate ligament, which I will illustrate later, ruptures 10 times more often than the posterior one, and half of the injuries that occur at the ligaments are at the ACL, so these injuries are very common. Additionally, sport is the main cause of those injuries, and it happens when the lower limb is fixed and a force is applied to the knee. For example, the knee is twisted or overextended, then the ACL can rupture. 3D printed supportive devices have already shown their benefit in patients with injuries in the collateral ligaments, the medial and the lateral collateral ligaments. And this review discusses that 3D printing, according to patients, has similar or in some instances superior performance in comparison to the existing conventional solutions. Lastly, the supportive devices, they are recommended by the physicians and they provide support during the recovery process, but unfortunately they are hardly affordable and they range between $300 and $800. So our main goal here is to create a 3D printed supportive device for ACL injuries based on a compliant mechanism that is easy to attach and customize and has a lower cost. The problems as mentioned here, there is a gap between the existing solutions on the market of the rehabilitation process. The transition between the devices is not smooth and the rehabilitation should happen very slowly. And also we need to control the loadings very carefully in order to restore the range of motion and the muscle function of the joint. So requirements of those kind of supports are to assist the motion in the main plane and in some instances to limit the motion at the early stages and to prevent out-of-plane motions such as knee valgus, torsion and overextension of the joint which are very important for ACO injuries, and the cost of the device, especially in our case. The targeted groups are all patients with ACO complications, and especially athletes, because they have greater requirements for them. So I will start first by introducing the rehabilitation process and how the existing devices don't reflect properly the gradual process of rehabilitation. So when the ACO is torn, more often a surgical intervention is required, and a replacement therapy is conducted to the joint. Later, I will illustrate this process. After that, at the very beginning, the joint is fixed, and the patient uses crutches to move around, 2 crutches, then a single one. And then the rehabilitation starts, where we very slowly and gradually increase the intensity of the exercises. And after that, for athletes, they start practicing their sports, but that happens very late in the stage. So following this blue horizontal line from after the surgery to fully recovered joint, the devices that exist are very few, and in between them, there is a risk for re-injury where the joint is especially vulnerable, and athletes can, when they start practicing more intensive tasks, they can re-injure the joint. And we are trying to address this gap in our work. This is a rehabilitation protocol developed by Juntendo University for athletes especially. So during the first month, we monitor if the knee is swollen and the level of pain, and we steadily increase the range of motion. Then for the first 3 months, 12 weeks, we increase the range of motion further. After that, the patient can start slowly jogging and running if the rehabilitation goes smoothly. And the next step for athletes around week 32, 34, they can start practicing their sports. Here you can see knee flexion and knee extension on the first top videos, and how we increase the range of motion slowly, and we provide some resistance. After that, hip extension and greater range of motion for knee flexion and extension, such as partial squats, as illustrated here. So on the top, we can see the rehabilitation for patients who are not athletes. All patients start similarly, and they use some devices that fix the joint, and then they start using the crutches and slowly rehabilitation. But for them, the rehabilitation process more or less ends, and they can go and start doing their regular activities. But for the athletes, it is a crucial step how they will continue their healing afterwards. So this is again data from Juntendo. We start increasing the range of motion, flexion and extension of the knee, provide some additional resistance. Then we include some lateral motion, because lateral stability is very important when the ACO is injured. And we increase the range of motion later by performing squats or other similar activities. And our hypothesis is that there is a room where such compliant devices can provide more flexible and safer environment for the rehabilitation to go smoother by slowly increasing the range of motion and slowly increasing the resistance of the on the joint to improve the muscular activity. First in initial stage for flexion and extension, and later for activities such as the squat. We will illustrate those later in the presentation. Additionally, another protocol is activity-based, not time-based, because it is the recovery is strongly individual and not always can be timed. And here, in order for the patients to proceed to the second step, they have to fulfill the criteria of the above one. Then they proceed, and the time doesn't matter whenever they feel comfortable and confident. We will later revisit this slide and show how it fits into our work. A little bit of the research work that has already been done on the field of orthotic devices. This is a timeline of the recovery process. First, we fix the joint, and later we allow greater range of motion until the recovery is complete. 3D printing has been used due to its customizability, but it has been used only in the initial stage for fixing the joint. It has not been used as a support to assist the recovery, but only to fix in the initial stage. And it can provide numerous benefits like high level of comfort and custom fit, but it's applied only at the beginning. Later, there are some mechanical solutions that exist, and such as this hinge one and a fabric one, such as the sleeves, but there is a huge gap between them, and patients can get re-injured while transitioning. They don't feel comfortable and confident. And for athletes, there is a high risk because they would like to start practice as soon as possible, and the joint is vulnerable during that period. Additionally, introducing one more axis, the supportive devices that are from static to dynamic. There are several dynamic solutions that provide actuation-based supports, but they are very sophisticated, expensive, sometimes bulky and heavy. They have their implementation and their place, but it is very specific and they are hardly affordable. And lastly, compliant mechanisms, which I will discuss a bit later, have been also implemented, but this is a relatively new field. And so far it is based more on try and error approach, and there is a lack of systematic methodology that describes and analyzes the function of those mechanisms for orthotic devices. This is a research review of 138 papers where the authors describe the angle, the moment, and the power absorption of the knee joint for non-injured joint during common activities such as walking, as illustrated here, stair climbing, running, and sit to stand. We have focused on the walking portion, and the walking, here we can see the time of the walking gait from the beginning to the end. It is divided into two phases, stance and swing phase, and they have their subphases. It is important, we will revisit these slides later. It is important to mention that the data between studies varies. So this is average data, and the peak moment that occurs is in the initial stage when we contact with the ground at point E. It is around 40 Newton meters. And the range of motion varies during walking between 53 and 78 degrees, depending on the studies. These are requirements that we have to fulfill later. So the knee is a complicated joint that it is not only a hinge joint that moves in 2 dimensions, but there is translation and a little bit of internal rotation of the lower limb. However, we have focused our research not on the medial and lateral rotation, but on the flexion and extension. And we have assumed that for those purposes, the knee is acting like a hinge joint. Ligaments, a few words about what they are. They are a collagen tissue that connects bones to bones and provides stability to the joints. And unlike tendons that connect bones to muscles, ligaments connect bones to bones. For the knee, we have the collateral ligaments on the outer side of the knee. They provide stability in lateral direction. We have the medial collateral ligament on the inner side of the thigh and the lateral collateral ligament on the outer side, the lateral side. Additionally, we have the cruciate ligaments. The name originates from their shape with respect to each other. They form a cross, and they are anterior, this one, and posterior behind it. So ACO and PCO respectively. Their name originates from the attachment on the tibia. The ACO attaches anteriorly on the front. PCO attaches posteriorly on the back of the tibia. That's why they are named like that. This is a short video that illustrates the knee replacement surgery. So these are the ACO and PCO. This is a normal functioning knee joint. But when a load occurs, the ligaments provide stability. But if this force is greater, it can rupture the ACO, and then the joint lacks stability. Then the joint is examined, and if surgery necessary, the surgeon makes few cuts to insert the instruments and the camera inside. Now I will discuss, based on those background, what our main focus has been. And we have focused on the implementation and development of compliant mechanisms, such as this one, into the supportive devices. Compliant mechanisms are those mechanisms that, unlike the traditional mechanisms, they do not rely on rigidly articulation, such as this pin joint, to perform the motion, but instead they rely on the deformation of a flexure to execute the motion. And the objective is to preserve the trajectory between the two models. And by making the mechanism compliant, that leads to several benefits, such as avoiding the assembly process and making the part lighter and more adaptive. So in our work, the approach we have used, we have started with a simple beam as a reference point, and we have varied and modified the hinging portion, the compliant part of it, by reinforcing, in some instances, reinforcing the models in order to provide greater stability at the bending point. And we have ended up with those 9 models, 8 if we don't count the beam, and the simple one. We have group A, in which we have removed geometry. These are common compliant mechanisms. Group B, we have added this kind of geometry, like a triangle. C, group C, is this half of a circle, and D is half of a polygon. And initially, we tried to estimate their properties by conducting a nonlinear finite element analysis. And the analysis has been done under the same conditions. The model has been fixed at both ends, and a force is applied in the middle. The force is equal for all models, and all models are, the properties of the material are the same for all of the models, similar to the TPU 3D printing filament. Here are some of the deformations for the models that deform largely. And this slide illustrates a comparison between all models. It is clearly obvious that they deform non-linearly, most of them, but for some, the loading was not great enough to deform them out of the linear portion. And this is due to the properties of the material and due to the high loading of the large deformation that occur. Here are the values of the displacement. We have organized them from the lowest to the highest, and we look for the models that provide the greatest level of deformation while the same force is applied, and preserving out of plane motion. We will see that later. And these are on the right side models, such as group A bar 2 and group C bar 2. They will provide the most flexible solutions. And inspired by this chart developed for estimating the efficiency of the different commonly used supportive devices based on the conditions, we have tried to evaluate our solutions depending on the range of motion they provide. Here we have 3 models that deform greater than the rest, but additionally, due to the nature of the ACL injuries, we have to provide stability in other directions. So these bars, due to their symmetry, they deform identically in all ways, so they cannot prevent torsion and out of plane bending. Therefore, a suitable candidate becomes group C bar 2, which is a flat planar mechanism and will provide better stability for out of plane motions. And this is the model we have chosen. Here is a summary of some of the points. We have developed compliant designs for application for orthotic devices, and the behavior has been analyzed in a nonlinear analysis in order to determine the ones that will be most suitable for an orthotic device. And group C bar 2 has been chosen as the most compliant one. Later, this model has been developed with the help of the Arizona company and printed from a PPGW material, which I will discuss later, and implemented into the assistive device shown here. And based on this mechanism, we have developed several more models that have common features, but different radius, different insertion angle, and different number of the flexures in order to determine, to create a group, a set of mechanisms. We need variety of them. All these models have been tested with the help of the artificial leg provided by Arizona. And here is the experimental setup. This is the artificial leg. It is a hinge joint in our case. And then we have a strain gauge, force gauge that measures the tension in the wire when we start pulling in that direction. And we measure the tension, and then we convert for the moments. And this will be the moments of the knee, the moments that the supportive devices can offload from the artificial leg. So first we measure for the artificial leg, then we measure artificial leg with the support and subtract the leg. So then we have the moment of the support itself. And it is important to mention that we have measured for up to 80 degrees knee flexion, this angle, theta, because for 90 degrees, phi becomes 180, and we cannot calculate the sinus is 0, and we cannot calculate the moment anymore. So we limit the range of motion up to 80, but as we saw at the beginning, during walking, the motion is between 53 and 78. So this will be sufficient, and also will be sufficient for rehabilitation purposes. And the hypothesis is, can our devices fill in the gaps between the existing solutions, between the hard hinge one and the sleeves, and provide smoother recovery. These are 3D printed models of the samples. And this is the measured data. So it's a raw format because it's a tension versus the angle or versus the displacement, and we need the moment. And according to the above equation, the moment has been calculated versus the angle. And this is a small illustration of where the angle and the moment are. And here is how we grade the devices. This is an important finding of our work. We increase the range of motion, which leads to the increase of the moment. And this is how we distribute our solutions. And as we can observe clearly, they fill in the gap between the existing devices. And if all those devices are used consecutively, one after the other, they will provide safer and probably faster recovery of the patients. This is our recommendation. And here are the values of the angles and the maximum moments. We can see that the maximum angle is the angle where the maximum moments occur is at around 75%. And also this slide shows that our solutions fit in between the conventional devices. And this is for a fixed device. And our solutions can be distributed throughout this range. Here again, we emphasize on their distribution, and additionally, more solutions can be generated depending on the individual requirements by varying the radius of the arcs and the number of flexures available. And this is our recommendation, how they can be implemented into the rehabilitation process. So we take the first peak moment, the initial stage. For the initial stage of the rehabilitation, all devices can be used one after the other for improving knee flexion concentrically and knee extension eccentrically. And then replace the more flexible one with a stiffer one, and then with more stiff one, and so on and so forth, until we have good control over the knee flexion and extension with the supports that provide greatest moments. Additionally, on next stage, once this is complete, we try to improve the range of motion and increase the forces that the quadriceps can generate. And this can be done with the second peak moment, which is greater. And here we are focusing on greater range of motion up to 80 degrees, which is a partial squat above parallel. And here we can start with the opposite way, with the hardest support, which will provide greater stability. Then when patients feel more confident, they can switch to a lighter one until they can squat without any external support. Then they can move on to the next task. And here is a short illustration of flexion with the support. And on the right side of a squat with the support. And they can be implemented in the already described principles of Tendo University. Moving on, this table, as we saw in the beginning, represents activities based on their level of completion. If the patient can complete one level, only then they can go to the second one. So we have focused on the first 5: walking, squat, single leg squat to parallel, landing during jumping, and running. And those activities can be distributed in such ways. We can use the devices to help support during them. Maybe from here it can be more clearly observed. The first initial stage where we have first peak moment that is lower, we can use the supports for activities 1, 2, and 3. And later, when the condition improves, we can move on to the next stage and use the supports for activities 3, 4, and 5. And after that, remove them and perform the activities without supports. So here is our main result. We have developed supportive devices that have been tested with the help of the artificial leg. The moments versus angles were measured, and it was illustrated clearly that they fill in the gap between the current existing solutions and can be used to enhance the rehabilitation process of all ACO patients and especially athletes. This slide illustrates the cost of the device. It is a rough estimation because it's not commercially available. The full cost is between $200 and $250, and this is how they are spread across the board. So it is a relatively cheap solution, and probably the cost could be decreased with the further development. But so far for the prototype, this is what we have ended up. PPGW is a material which has been already used for the development of orthotic devices, which means that it is bio-friendly and harmless to the body. And glass wool material is a recycled material. And here are some of the mechanical properties of the material. So far, we focused on the knee flexion and extension in our project, but we have to consider our motions. We have to prevent overextension and overloading of the joint, plus lateral stability. And this is illustrated here in those 4 steps as plans for future development. One way to achieve that, this is just an initial stage of the work. It's only illustrated, but tests need to be done. We can provide stability by modifying the cross-section as this I-beam, which will provide lateral stability, but keep the properties in the main direction of the flexion. Or we can create models that are made out of 2 materials, such as the more flexible TPU and stiffer PPGW. And here are some prototypes. They're very easy to assemble. They snap to each other, but this is for later stage. Now, second portion, which needs improvement, is regarding the walking support that the devices can provide. We have 2 peak moments during walking. In the stance phase, according to this graph, in the stance phase, we have peak extension around point E at around 40 meters in average, 40 Newton meters in average. And then there is a peak flexion point between G and H points in that range. And here is how the point E is calculated. These are the different studies that have measured point E. And so we average the body weight and multiply them in order to have the point E here. This is how the authors have calculated it. And in order to compare our results with the requirements during walking, we have to convert the angle into time. That comes from these slides. This one that is angle versus time. We convert it. We have already the angle, and we convert it in order to find the time. And this plot, moment versus angle, becomes moment versus time. And here we have 2 peak moments of the joints, of the supports, but unfortunately, due to the nature of the supports, they register the highest moment, all of them, even the commercially available solutions, the highest moment later between points G and H, which is less necessary, but instead we need the higher moment at around point E in the initial phase of the walking gait. Here we have support. There is another peak moment, but it is lower than this one. And in the future work, this has to be addressed. We have to combine this device with some additional actuation or some additional mechanism in order to address this issue and increase the moment here where it is the most required. Yeah, so as I mentioned, even the commercially available options face the same issue, the passive supports, and they have already been used for supportive devices during walking. They provide stability, but it could be further improved. And here is what I already mentioned, that the highest level the support generate is around 70% of the motion, but we needed at the beginning around 10. The findings of this are that we do provide stability during walking, but it has to be improved by implementing some external actuation to the joint and improve the knee flexion and extension moment at the initial stage. Although distributing the devices as illustrated before will still provide stability and help the walking gait of the patients and make them feel more comfortable. And in addition, these devices can be applied for different common activities such as sit to stand, stair climbing, and in which instances they will be more beneficial. So highlights is the adaptivity and adjustability of the models. They are very easy to attach. Then when another device is necessary, we remove the previous one and we attach another one. So that leads to greater level of customization. So additionally, they are lightweighted and low cost, relatively low costed. Materials used are harmless for the body. Limitations, more focus has to be, more test has to be conducted around point E. And additionally, more experiments have to be done for overextension and out of plane motion, and eventually some trials with patients so that they can give us their feedback how to improve. So with that, I would like to conclude my talk. We have developed compliant 3D printed mechanisms implemented for supportive devices. We generate their peak moment at around 70% and can support the walking gait by being interchangeable. But more importantly, they can support the rehabilitation process of the patient by being incorporated in some exercises and activities in order to support improving the range of motion and muscular activity for all ACL patients and athletes included. Here are the references I have used in the presentation, the publications in which I'm first author. And with that, I would like to thank you very much for your attention. And I will welcome your questions and comments. Thank you.
Thank you very much. So it's time to start Q&A. Please ask any kind of question. So, anyone, are there questions or comments or suggestions or something? Any kinds of questions are welcome. So, じゃあ、笠井さん。はい。Please、笠井さん。
はい。聞こえておりますでしょうか？
はい、どうぞ。
Can you hear me? So, Mr. Pancho, thank you for your nice presentation. And I have one question. So, please show me page, slide 49.
49.
Thank you. So, in your future development, you said it shows preventing knee lateral motion as a future development. And in your research, you suggest two-dimensional compliant mechanisms for plane motion. So, what model shape do you plan when supporting the out-of-plane motion, like lateral motion, lateral rotation?
Okay.
Is it adapting 3D shapes for supporting the movement, or is it possible to support with combining 2D shapes with a different characteristic on the left and right side of the knee supporter?
Yeah, that's a very important question. Thank you very much. So far, yeah, it's only the main motion of flexion and extension. We have assumed that it is just a hinge motion, which it is not. There is also translation with the rotation and internal rotation. It's a complex joint. In order to solve this problem, we proposed several new designs which have not been verified, but theoretically should help. But we have to fabricate and test them. One is by changing the cross section. As you know, an I-beam has different moment of inertia, will provide different information in different directions. One option. I don't know how greatly this will impact the solution. It will help to some extent, for sure. Another one is combining materials. First of all, we again change the cross section, and then we can manipulate the properties based on the material properties. And third one, this is work in very initial stage, is varying the mechanical properties of the 3D printing samples from inside. 3D printing is an additive process, and it's unique in its nature because you can control the model from inside. So we can start from lower infill densities and go to higher and see, also change the pattern, the infill geometry, and see how this will impact the model's behavior. But unlike any other technology, we can do that. So we have already tried to start this work, but it's in very initial stage, and we are just analyzing several models, but experiments need to be conducted, such as 3-point bending test. And we have adopted a cellular solid approach in order to address that for 3 types of infill and 7 types of infill densities. Then we will see how this will impact the behavior of the samples, starting with simple beams and then implementing it for the compliant model as well that you mentioned. So these are the proposed solutions so far. We will think for more improvements later, but so far this is what we have suggested, and it is yet to be tested. These are hypotheses, we don't know. So thank you so much for the question. I hope I have answered. If you
Thank you very much.
はい、じゃあ山崎さん。
はい、ありがとうございます。Thank you for your presentation. Actually, I had a ligament injury from playing rugby once, so that's why your presentation was so interesting. But I have one question. So 3D printers is not good for mass production. Are you thinking of printing this data at rehabilitation centers in the future?
That's very good question. Yeah, 3D printing is very good for customization, but not very productive. But we can, these devices, yeah, they can be, I don't think that the demand will be so high that the printers cannot reflect on it. And this is organizational matter that we haven't thought of, how they will be distributed and who will manufacture them. So far, we have focused on the design. Well, it's an important issue, yes.
You know, PPZW is a little bit difficult to print because it is the super engineered plastic. So the nozzle temperature should be more than 250,
yes.
Right? So that's why a little bit difficult to print. So why you didn't use PLA, ABS, or something more easier filament?
Yeah, those are common materials that we work with, and also TPU. But due to their properties, PLA and ABS are not elastic at all. They don't provide flexibility. And here you can see the PPGW. And TPU is very flexible, it's very elastic, it does not provide any support. And here you can see how the PPGW deforms. And is quite suitable for our needs. That's why we have chosen it. And also it has already been implemented for orthotic purposes.
Okay, I understand. Thank you.
Thank you.
Hi. Are there questions? Comments? Nothing. So, Mr. Pancho, may I have a question? Okay. Have you compared the materials other than PPDW or something?
Okay, so this has been done not for that particular purpose, but by many researchers. They have compared the mechanical properties of PLA, ABS, and their tensile stress, their Young's modulus, and we have not done it here because they are not suitable for that purpose. We have printed all the models, we have printed them from PLA and from TPU. PLA does not deform at all. It will break. It does not have good deformations. And TPU is very flexible. It cannot be controlled in any direction. It cannot provide any support. Very low stiffness.
Okay, thank you. そうじゃあ、ドンジョ、ごめんなさい、読めないんですけど、
どんどんじゃん。
ですよ。
DJ.
お願いします。
So, hello everyone, and thank you, Pancho, for your nice presentation. And I'm very happy to see you again on your final presentation. So, I have one question and one recommendation. And so, question is, how about the safety of the mechanism you proposed? Because the range of the motion was shown on the slide, but I wonder how it can be prevent the person from the flexion or overextension. So, because you propose kind of mechanism between static and the dynamic type, but I wonder how it can be prevent the person, because the human body is more sensitive, so this should be addressed. So this is the first question.
Should I? Okay.
Yeah,
DJ, thank you very much. And yes, so our range of motion is from 0 to 80 degrees of flexion. And this is sufficient enough for rehabilitation purposes, and the opposite way, overextension, becomes part of the future work. It is important for ACL injuries. You are right. So here, the second point below is what we will focus in the future. We have thought about implementing some additional mechanism that will stop and limit the motion. This is in development. It's not mentioned in this presentation because it's early stage. But that should be addressed. It's plan of the future work. And the safety that those solutions provide comes from their variety, because there are too many, so the recovery is very smooth and gradual. There is no room for the patient to be uncomfortable and feel not confident during motion. Yeah, overextension is part of the future work. That is.
Okay, so I see.
Short answer.
So what do you think? Probably it needs to be integrated with the dynamics. As you mentioned earlier, that dynamic, this kind of rehabilitation device has some kind of difficulty, you said, because of the controller and also complexity of the mechanism. But I think it needs to be integrated with some kind of active feedback controller, as well as some need of some sensor feedback to understand the behavior of the patient and the muscles activation during the recovery progress. So what do you think about this? Is it possible?
It is good point regarding muscle. Sorry.
So in the current moment, there is no sensor, real-time sensor feedback. It seems more like static, and how it can be shifted to the little bit dynamic side.
Okay, so it's a good point. It's important. First, muscle activation cannot be measured with any of these devices. It requires a laboratory environment, such as EMG or which will show the peak activation, or dynamometer. But this is in a laboratory environment. It cannot be done with external device. Next, we can think of some sensor that can measure the resistance and the resistance when it deforms, pressure sensor, and the range of motion, and see and monitor how the range of motion improves. But we cannot measure, unfortunately, the force directly. I am not very interested into into actuator-based solutions, because they are very complicated and very specific and very expensive. So we're trying to establish a more commonly accessible solution and a protocol how it can be implemented and used. But your point is valid and has to be considered. How to increase the moment around E point as shown here. Thanks a lot, DJ. I hope I have answered.
Okay, so thank you for your answer. So of course, the sensor feedback is most important point. We also think about kind of the center of mass during the rehabilitation process, how your the device will ensure the, how to say, the center of the mass of the moment, because the two-legged robot as well as human is very complex to ensure the stability during any activity. So you have to think about this, and I hope you will also have solution in the future regarding to these points. Okay.
Thank you, DJ. And yeah, the device can be used for experimental purposes with a motion capture system that will detect the motion of the person and compare to healthy individuals.
Okay.
And this will be great work, but for later stage.
Yeah, sure.
Thanks.
So thank you.
Yes. Hi. Are there any questions, comments, or suggestion, something?
Okay, so I have a question.
Please.
Yeah. So, Pancho, thank you very much for your quite very nice presentation. And please go to the slide number 57. Yes. Yes. So I think the discussion itself is great. And again, I would like to discuss about the part E in the last figure. And that time, I think Tachibana Sensei told us that so we need to take care of the shear force, shear stress, so occurred, so that can occur in the knee, right? And what do you think about, how to take care of shear force by the current, device, or some devices in your thesis?
So I think that, again, based on this paper, the walking gait is greatly influenced by the speed. So the device could be more helpful for walking with greater speed. Here in this table, you can see the average speed from the studies is 1.2 meters per second. And I think that
Yeah, I think that discussion
in
is
current
okay.
stage, yeah, it's more applicable if we use for greater speed walking. So what you mentioned, I think,
Right.
is
So in
is part of the future work, how to address the out of plane motions of the knee.
No. Just so Tachibana Sensei told us that So can you can you see watch what I'm doing? And this is a knee. And during walking, So there must occur shear force on the knee.
Yes.
You are talking about bending, flexion, extension, but shear force can occur on the knee during
yes.
the patient process. And so,
yes, Professor, thank you very much. I think that the nature of the device will address this by itself because it's a rigid device and it does not allow translation of the femur according to the tibia. So here is this motion.
okay, yeah.
Yes. So
Mhm.
I think the nature of the device address this issue because it is a rigid device. It does not allow translation of the lower limb forward.
Okay.
Thank
Thank
you
you.
very much, Professor.
はい。じゃあ、立花先生。
ありがとうございます。I will try to speak English today. So first of all, thank you for providing the valuable research result for the development of rehabilitation for patients after ACL injuries. In recent years, many robotic rehabilitation, robotic training has been developed as an advanced methodology. But I think it's also very important to have a method that addresses individual needs based on the complex structure and kinematics of the human body. So I also appreciate that your research is based on a very important perspectives in trying to solve the problem of responding to the individual needs of patients, who are changing day by day. So thank you very much. And I have one question. So I know the safety is a very important issue in applying this technology to the patients. So I'd like to know about the endurance or durability against the repeated stress of these 3D printed devices. So if you have any some supplemental data or any episodes, it's okay. Could you tell me with that?
Yes, so thank you very much, Professor, first for your comments. It means a lot to me coming from you as an expert in the field, that you value our work. And this is a very important question, the fatigue of the material, how it will affect the motion later. So we don't have such data, and we can use the same experimental setup and do a cycling motion and test many times the samples, but we haven't conducted such experiment yet. There is not much data available for the material fatigue that we can use. Instead, we have to conduct our own tests. But I think that if they're used in different stages for at least about 4 weeks or a month or so, the fatigue will not cause a significant impact because the time is not enough to fatigue to accumulate and deform the sample plastically. But this is yet to be tested. It's important, I know. So thank you.
立花先生、いかがですか？
立花先生、今のご返答
どうぞ、
いかがですか？
はい、 大丈夫です。何か、any
So,
comment?
my question is related to Professor Tachibana's suggestion and the comment. I think that you can explain here how your device can fit individual needs. How you can modify to fit some specific persons, the differences. Please add more the information against the Professor Tachibana's comment.
So we showed how the devices can be used here for different stages interchangeably, one after the other. And also, this is how they are distributed. In order to provide even further customization beyond already provided, we can modify some parameters illustrated here, such as the radius, the number of lectures, here is 3, it could be more, the insertion angle, the thickness of the sample, and those parameters will provide further customizability. And the time period that they will be used, I assume, will not be enough in order for the fatigue to become an issue, fatigue of the material to become an issue to deform the support. I hope that address.
Okay, you mean that I tried to confirm that your answer? Okay, there's some design have some principal parameter to change such a kinetic or dynamic property. So
Yes.
then if you set some target athlete, you can modify or adapt such a parameter to fit such the specific person, the athlete. Then prevent the overaction or to control the range of the dynamic property. That is your point, right?
That is correct. Thank you, Professor. So based on the person's body weight, limb length, the limb ratio, we can further customize the designs.
That's the most beneficial for your proposal because
Yes.
the robotic tool just provide one solution.
It's a single solution.
Universal, but you're focusing on the individual needs. That's why the design can be designed in the range of the specific person. That is your point, right?
That is true. Thank you.
Thank you.
はい。では、2個目です。questions 何かないでしょうか？質問、コメントなどですが。Nothing? なさそうですね。審査員の先生方、他に何かございますか？特によろしいでしょうか？よろしいですかね。はい。Are there questions? Nothing? Nothing. Okay. そう、じゃあ、柴田先生もじゃあ終了してもよろしいですかね。これで。良さそうですね。はい。わかりました。はい。Now, we'll close this defense.
Professor?
Okay.
I'm sorry. Before that, could I just say, I would like to thank very much to the evaluation committee for their valuable feedback and helping me improve the content of my work and their understanding throughout the evaluation process. I would like to thank my supervisor, Professor Wagatsuma, for his guidance and efforts throughout the process, and my lab members for being so supportive and friendly during the whole time. And I would like to thank finally to all participants for their time and attention. Thank you all very much. I appreciate your time and kind cooperation. Thank you.
Thank you. はい。
では終わりますかね。そう、みんな、じゃあ拍手で終わりましょう。はい。